worksheet, I just want to talk about a couple things. Oh yeah, you need to watch the video. We sent you a secret message. Not you. So if you listen to the last video, we sent a message to Colette. No, that would be a good way to get your phone taken away. YouTube. Can you do YouTube on there? Then yes. It just All right, I've I did a lot of thinking in my spare time about how to describe when you divide things off and when you don't. It's the one that's called poker odds. So um, let's consider 6 dice, and these are ones you should have done in your homework. 2 sets of 3. Okay? So I built this little system of possibilities, and we have set A and set B. Now, can I actually have 1, 1, 1, 1, 1, 1? No, why not? Why does that not work? That would be 6 of a kind, so that doesn't work. So I could do, oops, I just said you can't do that. No. So let's do it this way. Ah. So if I line those out, how many ways are there to pick the first digit? 6, and then 1, 1, 5, 1, 1. So there are, if I had a whole bunch of 1s, so here are some possibilities. So 1, 1, 1, these are all 1s. Okay, so there are 5 possibilities for that, right? 1 with all the other numbers, and then you could have 2 with all the other numbers, and 3 and 4 and 5 and 6. So this 5 here is represented in that group. And how many groups of that size are there? Well, 5 more. But there are 6 of these groups. 1, 1, 1, 2, 2, 2, 3, 4, 5, and 6. So there are 30 ways to create a group where you have group A and then group B, lined out in this fashion here. But that's not the only way to create 2 sets of 3. What would be another way? So let's think of a combination for this. How could you rearrange that? 1, 2, 1, 2, 1, 2, or 1, 1, 2, 2, 1, 2. Or you could do, what about 2, 2, 2, 1, 1, 1? Well, we're not done, so hang on. Okay, so now what we need to do is reorder the 2 groups. Okay, so we'll call this group A and this group B. Right, and here's where it gets tricky. How many ways are there to place the digits in group A? 6, choose 3, because there are 6 spaces, and we want to fill 3 of the spaces with the same number. Let's say we want to fill 3 of the spaces with 4s, for example. Well, there are 6 choose 3 ways to do it. What about the second group? 3 choose, well, there are 3 spaces left, and what is 3 choose 3? It's just 1, so we can ignore it. Once you place the second to last group, the last group is already chosen for you. Agreed? But this number is too big. And here's the reason why. If I create 1, 1, 1, 2, 2, 2, and I pulled this from A and I pulled this from B, is that the same thing as pulling 1, 1, 1 down from there and pulling 2, 2, 2 down from there? Yes, I've been hearing it all day. So, are these 2 groups equal? Hey, I'm losing you. I know. Thanks, Connor. So, are these the same number? Yes. Did they both get counted? Yes, because we said there are three ways, there are six choose three ways to place A. But what if I accidentally count AB and BA? So can you see that I've included too many numbers? Because if I set A here and I set B here, that's no different than B and A. And in fact, if I had like A1, B1, A2, B2, A3, B3, is that the same as B1, A1, B2, A2? So in this case, the order of A and B does not matter. Now this is really tricky because that is a permutation, right? Because order matters when you're rolling dice. This is a combination because the numbers inside A, the order does not matter, right? It doesn't matter if I do A1, then B, A2, then A3, because A1, A2, and A3 are all the same digit, right? So that's a combination because the order of the group doesn't matter. But this is a combination because the order of A and B does not matter. But I counted it as though it was a permutation, which means I need to divide off the number of choices, the number of combinations of A and B. Okay, and that's not going to make a lot of sense right now, but hopefully it will. So we know that AB is identical to BA, and what is it about those two groups that makes that true? Why are A and B counted the same? There's something inherent about them that makes that the case. I might have lost you in all of this. Why are A and B interchangeable? They're the same size. That's why. They both have 3 in them. So, how many options do I have for the first group? 1 in 2. So there are 2 options here and 1 option there. Well, we're not talking about the numbers. Okay? We calculated the permutation. That's done. We calculated the number of combinations for arranging A and B, but we overshot. We overshot because AB and BA can be the same thing. So this tells us how much we overshot by. Our answer is twice as big as it should be. So we need to take this is 30, and this is 20, times those together, 600, and we divide it by 2, and the answer is 300. Okay, now let me do it again, and it will make a lot more sense the second time. So we're going to look at, actually, let's do this. So we're going to look at 3 pairs. Give me the breakdown for the number of possibilities for one arrangement of the pairs. 6, 1, 5, 1, 4, 1. So for example, that would be 1, 1, 2, 2, 3, 3. So 5 times 4, 6 times 5 times 4 is 120. So there are 120 ways to do that. Now, we could rearrange the digits. We could do 1, 2, 3, 1, 2, 3, or 1, 1, 3, 2, 1, 3, 2. So how many ways are there to mix those numbers up? Keep the same digits, but you can reorder them. Well, we have 3 groups, right? How many ways are there to place the first group? 6, choose 1. 2, sorry. 6, choose 2. You don't remember when I wrote that? Year before. Thanks, Connor, for interrupting again and getting everybody off task. Okay, how many ways are there to reorder the second group? Does everybody understand that? The first two numbers, so the ones. I can place the ones in 6 choose 2 places. Once I have placed the ones, how many places can I put the 2s in? 4 choose 2. And what about the 3s? They're already decided. And because they're the same, it doesn't matter which one goes in which place. Okay, so 6 choose 2, I believe, is 15. And 4 choose 2 is 6. So 120 times 15 times 6. But where did those digits come from? Okay? Where did these digits come from? What group? It came from A and B and C. But is that the only way to create 1, 1, 2, 2, 3, 3? No. I could have pulled the 1s from B, and then pulled the 2s from C, and then pulled the 3s from A. Are those numbers duplicates? Yes. They're exactly the same number. We're looking at a 6-digit number. But because there is a possibility of changing those orders, we have already counted it twice. So the question is, how many extra times did we count it? Well, let's break it down. There are 3 sets. How many options are there for picking the group in the first set? So we're looking at Group A, Group B, and Group C. There are 3 ways to pick it. Once I've chosen that, how many are left? Times 2 times 1, which is 6, and 3 times 2 times 1, by the way, is 3p3. So what does this number tell me? I counted every number 6 times. So my answer is 6 times larger than it's supposed to be. Because there are 6 ways to do 1, 1, 2, 2, 3, 3. And there are 6 ways to do 1, 1, 3, 3, 2, 2. Because you can pull them from those different groups. So to even it out, you have to take this 120 times 15 times 6 and divide it by 6. And your answer is going to be 120 plus 60, 180. Does that sound right? So does that make any more sense than it did yesterday? So that you know. And again, I really struggle with this stuff, so I totally understand. I've been teaching this for a couple years, and I understand this worksheet a lot better, but you throw something new at me, and it really is hard to do. Okay, well, let's look at something that we've seen before. What if we go back to 5 dice, and we do a full house? So a full house would be like 3, 3, 3, 2, 2. So let's say that we have Group A and Group B. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is my full house. Is Group A then Group B the same as Group B and Group A? So let's pick a digit in Group A, a 2. Let's pick a digit in Group B, a 5. Is 2, 2, 2, 5, 5 the same as 5, 5, 2, 2, 2? So if this is my triple and this is my pair, are those interchangeable? No. 3, so 3, 3, 3, 2, 2 does not equal 2, 2, 3, 3, 3. Or you could look at it the other way. 2, 2, 2, 3, 3. Either way. But you see how when the groups are different sizes, you don't create duplicates? Because if I wrote 3, 3, 2, 2, 2, are those two groups the same? No. But what if I knock off a 2 and a 3? Now they are the same. So in this format, it's really easy to tell which one is A and which one is B. Because the A is a set of 3 and the B is a set of 2. But if I erase one of those numbers, oh my goodness, what is going on? Okay, it's haunted. If I erase those, now can you tell A and B apart? Now you can't, so both of those get cut, get counted, and so it's kind of a mess. Okay. And I'm not going to ask you any question like that on the test, but some of you, this really works, and you'll move on and you'll do some statistical stuff. Me, it's not for me. I'm not any good at it. Okay. How many of you have been introduced to Pascal's triangle? What is the pattern in Pascal's triangle? Oh, good. Hey, I'll do the easy one. Those are all ones, and those are all ones. So, and just so we're all using the same language, we're going to call these rows. Okay? And these are diagonals. So the first diagonal is all ones. The second diagonal, 1, 2, 3, 4, 5, and so on. We'll talk about that. How can you generate new numbers? So if you look down at your chart, what's the pattern to create numbers? Good. So 3 and 3 make 6. 1 and 3 make 4. And then these are always ones. So this pattern is 1, 2, 3, 4, 5, 6, 7, 8, 9. What's this number going to be? 10. And notice that they mirror each other. So if you start on the ends, 1, 1, 5, 5, 10, 10. So the one below the 5 and the 10 would be 15, 20. And now, once I've passed the halfway point, I just count back down. 15, 6. 6 and 15 make 21, 35, and I'm halfway. 35, 21, and 7. Any two numbers add to be the number below it. So 7 and 21 make 28. Well, if this square is 28, then this one has to be 20. Oh, this one has to be 28. And this is an 8. Well, that's got to be a 9. 28 and 8 is 36. And if I have a 36 on one side, got to have 36 over here. 21 and 35 is 56, so there's got to be another 56. And 35 and 35 make 70. 126, 126. So that's 84 and 84. Okay, let me show you some more patterns that are kind of nifty. If I look at the first diagonal, it is constant. Constant meaning it doesn't change. There are no difference in those numbers. Let's look at the second diagonal. What type of formula would create the second diagonal? Linear. Why is it linear? Because my first difference is plus 1, plus 1, plus 1, plus 1. They all differ by 1. Okay? What about the third diagonal? So let's look at the differences. Plus 2 plus 3 plus 4 plus 5 plus 6. So this is my first difference. And my second difference is going to be plus 1 plus 1 plus 1 plus 1. So my second differences are constant, which means that my original equation would be quadratic. Okay, so let's look here. So we have, so I'm just going to write 1, 4, so I can see this a little bit better. 10, 20, 35, 56, 84. So this is plus 3 plus 6 plus 10 plus 15 plus 21 plus 28. So these are my first differences. These are my second differences. My third difference, plus 2 plus 4 plus, oh, wait a minute, I messed up somewhere. Oh, that's a 3. Oh, wait, these are wrong. First, second, and this will be third. I'm just subtracting every time. What's the difference between any two numbers? Then I have plus 1, plus 1, plus 1, plus 1. So this was my original row, my diagonal. These are first differences, second differences, third differences. So therefore, this equation is a cubic equation. And if you notice, this is an x to the third, x squared, x to the first. What about a constant? X to the 0. No. Yeah. Okay, well, guess what? I totally wasted my time writing all these differences out because this is that column, but my my first differences actually match my quadratic column. And my second differences actually match my linear column. And my first differences actually match my constant column. So if we looked at the seventh, well, really the eighth diagonal, because you have to count 0. So here is the eighth diagonal. When I do the differences, I'm going to end up with those as differences. So those would be first differences, second differences, third differences, fourth, fifth, sixth, and seventh. So the eighth diagonal is actually an x to the 7th equation. So the Pascal's triangle actually includes all of the differences in the diagonals. Okay, well, we're not going to use that for any of this kind of stuff, but we're going to do something different. See if I can get rid of most of these. Oh boy. Well, I can just clear it out and go back to the top. Okay. Look at this row. Have we ever seen those numbers before? Where have we seen the numbers 1, 5, 10, 10, 5, 1? No, you're close, but it's not it's a combination. Remember back when we had 5 books and we were taking them to school? So if we have 5 books, how many ways are there to take none of them to school? 1. You leave them all home. Well, how many ways can you take none of them to school? 1, because if you take any of them, that one doesn't count. So how many ways are there to take 1 book to school? 5. If I have 5 books, I can bring book 1, book 2, 3, 4, or 5. So notice, I guess technically you could tear your book up, but then you'd have to pay for it. Of course, in math, we don't believe in textbooks anymore. What about 5 choose 2? No, no. So 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. So there are 10 ways to take 2 books to school? Some of you aren't paying attention back there. How many ways are there to take 3 books to school? Why is 10? 2 and 3 add up to 5. If you take, my goodness, if you take 3 books to school, you left 2 at home. So by choosing a group of 3, you already choose a group of 2. So 2 and 3 are interchangeable, just like 4 and 1, and 0 and 5. How does what make 10? So there are 10 ways to take those books to school. Everybody agrees. Well, I could write out the possibility for 3. 1, 2, 3, 1, 2, 4, 1, 2, 5. But why don't I just say, okay, this is the number of ways to take 2 books to school. If I take 3 to school, then this is the number of ways to leave 2 at home. And it's the same number. And in Pascal's triangle, those match, and those match. So your highest numbers are always in the middle. So what does this tell us about combinations? All possible combinations are in Pascal's triangle. Every n and every r you can think of are in the triangle, as long as you extend the triangle far enough. And there are lots of other patterns. So I just told you what that was. Yeah. You were waiting and waiting, and then okay. So some of these rectangles are black and some are white. What's the difference? Take a look. Right, the black ones are odd and the white ones are even. So watch this nifty pattern. You start with an odd, and the odds go all the way down the sides. So if I take this odd and put it there and there, now I create a little red triangle. Now I take that red triangle and I move it down. So I put that triangle here and here. And then whenever the triangles create a gap, that gap is filled by even numbers. So now that creates a bigger triangle, and those triangles are duplicated here and here. And notice that inside is full of nothing but even numbers. Now, well, don't look at the numbers, look at the colors. So this triangle gets put here and here, and the inside is full of nothing but even numbers. Now, I can take this big triangle. I don't know what's going on today. So, right. So, can you see? Hold on, we're running out of time. I don't want to have to give you homework. Can you see how there's going to be a huge triangle, upside down triangle with nothing but even numbers if we were to continue that down? Okay, so let's think about it. Let's look at this set right here. Why are there so many even numbers in a row? Because the ones, okay, we could use the triangle pattern, but let's look at it numerically. Right. The row above is nothing but odds. And what happens when you add 2 odd numbers together? Makes an even number. Okay, why was that row nothing but odds? So if you look at the row above, black, white, black, white, black, white, black, white. Okay, so here's another question. This large, even-numbered triangle that continues down, why is that triangle getting smaller every row? Wow! Aren't you glad you don't have a mic? Why are the even numbers getting smaller? No. Good. Good. And when you throw in the word people, so on the edge, it's so on the edges are always odd. So when I add those edges, the one below it is going to be odd. And now I have an even odd pair again, but that even odd pair has gotten closer together. And so it's going to be a bunch of white rectangles going down in a triangle. Now, of course, inside this part of the triangle, there will be evens and odds. But this big triangle here is going to get smaller and smaller and smaller, and then that pattern continues. There's got to be more blacks. Well, I don't know. That's a good question. Look it up. That's your homework. Okay, so the first question says, if you start with 8 different paint colors and you mix 2 colors at a time equally, how many colors can you create? Why did I put the word equally in there? How many would there be if it wasn't equal? An infinite number. Supposing you had an infinite number of paint, right? You could add 1 paint molecule or 2 paint molecules or 3, up to an infinite number of paint molecules. Okay, so what we do is go to row 8. But what does this number represent in terms of a combination? What choose what? It's 0 choose 0, which is 1. So if you have no books, how many ways can you bring no books to school? But you only have choices, bringing something and not bringing something. So it is a little bit silly, but trust me, 0 choose 0 is 1. So this is actually row 1 right here. And the top one is row 0. And the same is true of diagonals. Diagonal 0, 1, 2. So if we want 8 choose 2, then we have to go to row 8, which is actually the 9th row, but it's the row that has 1, 8 in it. And then we go to diagonal 2, which is, because remember, the first number is from 0. Well, it counts as a 0. Right, right. Okay, so 8 choose 2 is 28. We're running out of time, so let's go to number 5. If 14 people are left in American Idol and 2 people get the axe each night, how many ways can a group of singers be left after 4 nights? Combination or permutation? You're both right. It's a combination each night, but the nights are a permutation, right? So I'm gonna knock 2 people out the first night. Does the order matter? No, they both lose. I mean, technically, somebody loses first and second, but they both lose. Okay. The second night, I'm gonna knock 2 people out. Are these 2 nights interchangeable? No. So we need to do a combination and a combination and a combination and a combination, and then do we add them together or do we multiply them together? Well, combinations add and permutations multiply. No, so we're going to calculate the permutation for night 1 and night 2, but those nights are not interchangeable. If I lose the first night, that's different than losing the second night. So if you lose, if that matters, then you multiply. So how many ways are there to pick the losers on night 1? 14 choose 2. So we go to row 14, and we count off 0, 1, 2, 91 ways. So 91 times, how many ways are there to pick the losers for night 2? 12 choose 2. So I go 12, 0, 1, 2. 66, and knight 3. 10, choose 2. So 10, 0, 1, 2 times 45. And then 8, choose 2, which is 28. So if I were to say something like, there are 14 people, and I'm going to choose 8 of you to go on a trip, but I'm only going to pick 2 per day, then are you going to multiply all these out? No. Because really, it would just be 14 choose 8, right? Yeah, that would make things worse. Okay, make sure you look at number 8. That's Connor's problem from 2 years ago. And by crazy hot, Connor means crazy and hot. Not like insanely hot. He means crazy and hot. So, um, so number 9 and number 10 are a 4-card poker game. Remember, when you calculate those, you do suits and numbers separately. So you calculate the possibilities for the numbers, and you multiply it by the possibilities of the suits. Okay? Good luck.